In a previous video, we talked about developing a sampling plan, and we did some calculations for determining the sample size, specifically in that case, to designing a survey. How do you figure out, based on your questions, how many people need to respond to your survey? And the key here was, if you have too large of a sample, you're wasting money on trying to get more people to respond. It's more time banging on doors, pleading with people to answer your survey, as we were talking about. But if it's too small, then you have a lot of error and your sample doesn't represent the population. And ultimately, we want to take the information from our small group and extrapolate it and make some statements about that bigger population. So too small of a sample increases the sampling error. Now, ways we can mitigate the fact that, or make sure that our sample represents the population. One, a probability sample. We use a method, and we've talked about those in previous videos, where while we're chatting about it, let's just flash back to that real quick. Systematic, stratified, cluster, simple random sampling, all methods to ensure that you are taking and selecting that sample at random from the greater population so that there's not additional bias and so that that variability in the population is represented in the sample itself. The other thing to make sure you can extrapolate from your sample to the greater population is to have a bigger sample size so the variability that's in the population is reflected in your sample. And we've been talking in the last couple videos about how the fact that every time we take a sample, we get different, say an average. All right, if we take a sample of a group and we find the average age, the next sample is going to have a different average age. So those sample statistics like averages and proportions, they vary. They are a random variable. They have a sampling distribution, which is what we talked about in our last video. Well, here we're talking about sample size as it relates to that. And so just calling you back to a previous video where we talked about determining sample size and we did a number of calculations. So what we're going to do is further our discussion here about sample size by continuing the conversation we had in the previous video about sampling distributions and the central limit theorem. So we had just talked about that when it comes to a sampling distribution, if the population from which the sample is drawn, so if the ages have a normal distribution, then the distribution of the sample means, so the average ages, will also have a normal distribution. And we talked about that if the population from which the samples are drawn is not normal, then if the sample size is large enough, the sampling distribution will be approximately normal. And so this is important, and it helps us build to the central limit theorem. The central limit theorem says if random samples are selected from a population, and remember these population parameters are unknown, we're trying to estimate them, the mean mu and some finite standard deviation sigma, then as the sample size increases, then the distribution, as we plot our sample distribution, we plot all these different averages, it's going to start to look like a normal distribution. And that normal distribution is going to have where the average of the averages, so this center right here, this average of the averages, will be that population parameter, the mean mu. And so we are getting to estimate mu and sigma with our sampling distribution, as long as the sample size is sufficiently large. So it really doesn't matter what the original distribution of the data looks like, as we stated in that, that was the statement we made right here, as long as your sample size is big enough. So here's some examples. So here's some different distributions. The underlying data, here's uniform, we have skewed. Notice that none of those distributions are normally distributed. But notice that as we take larger and larger sample sizes, that the sampling distribution, So we're looking at pulling samples from this underlying population. So we pull a couple of the x's, we find the average of the x's, we get x bar. Notice that as you get a bigger and bigger sample size, you start to get a normal distribution. So how big is big enough? Now, if you are reading like an intro stats textbook, they will typically tell you the general rule of thumb is 30. So we think about this, what does this mean? This is essentially saying that if I am going to compare if I want to know the average age of people in central Alberta, I pull a sample of 30 people in Alberta and take their average age. We take into consideration the sampling distribution, we could find the average age of the population. Well, this general rule of thumb we often use in intro stats is really too rough of a rule to be useful. It's kind of like the bare minimum. But really what you should think about is that underlying data, how skewed is it? Is it normally distributed, where the mean, the median, and the mode are about the same, where there's an equal number on the high end and the low end? The more the underlying population has that normal distribution, the more you can get away with a smaller sample size. The more skewed the population, like when we talk about like these here, the bigger the sample size needs to be. Okay. Now we're talking here about this kind of general rule of 30, but as we measured with the different types of questions we might ask, then we are looking at potentially a lot more than 30. So I refer you back to the video we had about sampling size and the difference between if you have questions that are proportions questions, so we are going to summarize them with proportions. These are nominal type questions where we're identifying categories and then we're summarizing it based on what percentage fall in those different categories. Those need a different sample size than questions we would summarize with a mean, like how much do you spend? In this case, we're looking at the average spending on fishing trips. They would require a different sample size. And so you do this test for different types of questions, and whichever the bigger number is, you go with that one for your minimum sample. What we want to point out here, as we continue our discussion here in the statistics, is that the sample is also going to depend on what does that distribution look like of the underlying data. If your underlying data has more of a normal distribution naturally, you can get away with less. In terms of your sample, the more skewed it is, the higher the sample size needs to be. And that's because of the central limit theorem that says bigger sample sizes will get us closer to that normal distribution where we can then estimate those parameters. Okay. So how big is big enough? Well, you should always look at the histogram of the data for your sample before deciding, or histogram of previous information collected from that population. What do you already know about that population before you are deciding which sample size is large enough? Okay, so it is a bit of a judgment call. If your histogram of your underlying data is highly skewed, then the distribution you sample from will also be skewed, in which case you're going to need a bigger sample size. As I said, what we tell people in intro stats is minimum 30. So if we're doing forecasting, we want 30 data points. We forecast into the future. If we are doing a regression model and trying to say, okay, well, here's the temperature, here is, I don't know how many bugs there are, density of bugs, right? And we're trying to do a prediction in terms of how temperature relates to the density of bugs. You know, we want at least 30 data points, 30 different temperatures and the number of bugs that go with them in order to build those models. So minimum 30, that's kind of the basic rule of thumb, but it is very rough of a rule. And what we really want you to do is think about when we're doing things like surveys, that there are ways to calculate what that sample size should be. and to consider that underlying shape of the distribution in that population is also going to indicate whether you need to up the number in your sample. So the central limit theorem here on the mean of the sampling distribution, what we found is that our mean, and you can't see it because my face is covering it, but you can see here that the average of the averages really did start to get to that population parameter mean, and that was with a sample size of 2 in that case. We get to that point. And that would be looking at, well, what was the original distribution of the data? How normal was it already? So the other thing we need to know besides the central limit theorem is this idea of the law of large numbers. The law of large numbers says the larger the sample size, the more probable it is that the sample mean comes arbitrarily close to the population mean. So think about it this way. If you took a census and you surveyed everybody about their age, then your sample is equal to your population. So you interviewed everybody, in which case the average from your sample and the average from your population are the same because they're all the same people. Well, what if it's not quite everybody? So there are 1,000 people, you get a hold of 800 of them, and you get the average of 800 people instead of 1,000 people that would have been the whole population. Well, because you're representing most of the people, the average age in your sample is going to be really close to the average age in the population. So the law of large numbers says that the larger the sample size, the closer your sample statistic is going to be to your population parameter. Okay, now that's great, but if I could survey everyone in the population or everyone in the population minus 2 people, well, why wouldn't I have just done the entire population anyway? So the law of large numbers says larger sample size gets us closer, and then we combine that with the central limit theorem, which says that, okay, well, bigger samples get us closer, but the central limit theorem also tells me that smaller sample sizes will get me to, oh goodness, right? That if they are truly random samples, so they are probability samples, then I'm going to get that normal distribution. So law of large numbers, a big sample will get me that population parameter. If I can't get a large sample, I have small samples, but I identify that sampling distribution. That sampling distributions, the average of the averages, will also get me the population parameter. So through the law of large numbers or through the central limit theorem, I can get to estimating what that population parameter is. Either a sampling distribution of all the samples or really large samples. All right, where was I in the grand scheme of things? Okay. So standard error is the standard deviation. So let's just be clear. Sampling error is the difference between your sample statistic and your population parameter, how far apart they are. So we're looking at what's the difference between mu and x bar. That is going to be our sampling error. Yep. Standard error, so just make sure we're differentiating between. Standard error is going to be the standard deviation of the sampling distribution. So we take all our x bars, our average, the average of the averages gives us mu. How much variability there is in that sampling distribution, that standard deviation has a special name called standard error. So it's measuring the variability in your sample statistic. Every time you take a sample and you find the average of that group, those are different averages in each sample. How much do they change from sample to sample? So standard error is measuring how much each time we take a sample and find the average age, how much it's different. According to the central limit theorem, as the sample size increases, the standard error will approach the standard deviation. So the central limit theorem, remember, says that our sampling distribution, the average of the averages, is going to give us the population mean. The standard deviation of the sampling distribution will give us standard error, which is the standard deviation of the population. Okay. Standard deviation of the population. Standard error approaches the standard deviation of the population divided by the square root of the sample size. So it's not quite the standard deviation of the population. There is an adjustment for the sample size. So the size of the standard error is going to be affected by the standard deviation of the population. It's going to be affected by the sample size. As the sample size increases, your standard error is going to decrease. The bigger your sample, the less variability in the averages you take because you're really covering everybody in the population. So it's not going to vary as much. The standard error is going to be smaller and smaller. There's less variability in the sampling distribution than there is in the population. So if we are comparing averages from multiple samples, they are not going to vary as much as the underlying data itself. So for example, if we go back to the households original data. Okay, so you can see here we have a household of 1 and we have households of 4 and 5. So the biggest swing, right, is between a household of 1 and a household of 5, so 4 apart. If we look at the averages, notice that the biggest average is 4.5, and the lowest average is 1.5, which is only a difference of 3. So what this is saying here is that the sampling distribution, so if we're looking at all the averages, they don't vary as much as the underlying data itself, which was the number of children per household. And that makes sense because an average is a summary, a central tendency. You know, it is summarizing the information, all the variability in the underlying data to a central point. And so then our means are going to remove that variability that's in the underlying data. All right, where are we? Here we go. Less dispersion in the sampling distribution than there is in the underlying population. Oh, look, I could have just done it from here rather than do it back there. So this is calculating the standard error for the family size example. Here we have the average, and the mean we found was 3. Standard error, we are taking, it is the, remember it's the number minus the average, so standard deviation measure, right? So it's x minus mu squared divided by n minus 1 square root. We looked at that standard deviation before, and that's all that's happening here is the difference between taking the square, adding them all up, and here, because there are 2 in this frequency, then it's 2 of this number if we're adding them up, 1 plus 1. That's this extra piece here. There were 3 of the difference between 2.5 and 3, so that's why the 0.75 in the formula to get that standard error. So standard error is just the standard deviation of the sampling distribution, which means the formula is the same formula for standard deviation you saw before. It should be x bar. The difference here is that we are looking at x bar instead of x's, and so this becomes x bar and this becomes mu. And sometimes this is listed as standard error. So the variability in the averages. The population standard deviation, the difference between population and sample, when it comes to standard deviation, we talked about this before. We're not dividing by n minus 1, we're just dividing by n. And so here the population standard deviation is found to be 1.29, taking each household, their number, minus to find that population standard deviation. So when we compare the population standard deviation and the standard error, the population standard deviation, we got a bigger number than the one for the sampling distribution. There's less dispersion in the sampling distribution than there is in the population. Now we only had a sample size of 2, and so if we adjust this for that sample size, and you can't see that because my head's covering it up. So one of the reasons the central limit theorem did sigma divided by square root of n is that you can see when you do this additional adjustment for the fact the sample size was only 2, it pulls this number down, pulls this number up to 0.91, closer to that population parameter of the standard deviation. So it's making an adjustment for the fact the sample sizes were small. All right, so wrapping up this discussion in this video here, we have been talking about the central limit theorem and the law of large numbers, and how the larger the sample size, the closer our sample statistic will get to the population mean. And if we don't have super large sample sizes, but we use a sampling distribution, then the average of the averages will get us that population mean. And we can also use that central limit theorem to get to the standard deviation with an adjustment here for the sample size, for the fact that the sample statistics and our sampling distribution is going to have less variability than the underlying population. And so we have to take that into consideration and do that adjustment. Again, what we're trying to do is we're trying to estimate what is happening in the bigger population, because those population parameters like the mean, like the standard deviation, they're unknown. All we have is our sample statistic. And so bigger sample sizes and sampling distributions will get us closer to that population parameter. We also talked about how bigger samples will get us that normal distribution. So at bare minimum, we're talking sample sizes of 30. If the underlying population is more normal, you don't have to have as big of a sample size. The more skewed the population, the bigger the sample size. And in previous videos, we talked about, depending on what kind of parameter you're trying to estimate, whether it's a mean or a proportion, that's also going to impact what the appropriate sample sizes are.